In this video, we're going to look at a few more examples of estimating the sum of an alternating series. For the following convergent alternating series, find the smallest number of terms that have to be added up so that the error is less than 10 to the minus 6, 10 to the power of minus 6. That means 5 decimal place accuracy. Question A, summation n equals 1 to infinity, negative 1 to the power of n, divided by 10 to the n times n. Question B, summation n equals 0 to infinity, negative 1 to the power of n plus 1 times 1 divided by 2n factorial. Let's look at question A first. We have summation n equals 1 to infinity, negative 1 to the power of n times 1 divided by 10 to the n times n. Let's check the conditions for the alternating series test to prove that it converges before we can apply the remainder theorem. So condition 1, the terms have to be decreasing in magnitude. an plus 1 should be less than an. Let's show that. an plus 1 is the n plus 1th term, the absolute value of the n plus 1th term. We get 1 over 10 to the n plus 1 times n plus 1. And this should be less than the nth term, which is 1 over 10 to the n times n. Clearly, we're making the denominator larger. That means the ratio becomes smaller. So the first condition is satisfied. All right, let's check the second condition. The second condition for the alternating series test is that the limit as n approaches infinity of an should be equal to 0. So the limit as n approaches infinity of 1 divided by 10 to the n times n, clearly this limit will approach 0 because in the numerator we have a constant, in the denominator we have 10 to the n times n, which grows to infinity really fast. A constant over a huge number is going to approach 0 as n approaches infinity. All right, so both conditions of the convergence test are satisfied. This alternating series converges to a finite sum. So now we have to apply the remainder theorem to find out how many terms we need to add up such that we have 5 decimal place accuracy for estimating the sum. So the absolute value of Rn is equal to absolute value of s minus Sn. And this is less than or equal to the first omitted term, which is an plus 1. And we'll make this less than 10 to the power of minus 6, 0.0000005 zeros and a 1. So an plus 1, the n plus 1th term, is equal to 1 divided by, substituting n plus 1, we get 1 over 10 to the n plus 1 times n plus 1. And we'll make this less than 10 to the minus 6. All right, so we have an plus 1 is equal to 1 divided by 10 to the power of n plus 1 times n plus 1 is less than 1 divided by 10 to the 6. So let's try n equals 4. If we try n equals 4, plug n equals 4 for n, we get a5 is equal to 1 divided by 10 to the power of 4 plus 1 is 5 times 4 plus 1 is 5. And this is larger than 1 over 10 to the 6. So n equals 4 does not work. Let's try n equals 5. n equals 5 gives us a6, the first omitted term, if we add up the first 5 terms. So a6 will be 1 divided by 10 to the power of n equals 5, plug that in, we get 5 plus 1 is 6, times 5 plus 1, which is 6. And this is definitely less than 1 over 10 to the 6 because we've made the denominator of the left-hand side is larger than the denominator of the right-hand side. Hence, the ratio on the left-hand side is less than the ratio on the right-hand side. So n equals 5 works. So that means we need to add up the first 5 terms of this series to approximate the sum of this series with error less than 0.000001 or 10 to the minus 6. So S5, the sum of the first 5 terms will be summation n equals 1 to 5, negative 1 to the power of n, divided by 10 to the n times n. Plug n equals 1, we get negative 1 divided by 10. N equals 2, we get 1 divided by 10 squared times 2. N equals 3, we get negative 1 divided by 10 cubed times 3. n equals 4, we get 1 divided by 10 to the 4 times 4. And n equals 5, we get negative 1 to the power of 5, that's negative 1 divided by 10 to the 5 times 5. So if we add up the first 5 terms, the error of approximating the sum of the entire infinite series is going to be less than 10 to the minus 6. All right, so that means S minus S5 will be less than 10 to the minus 6. All right, let's look at number B. Here we have summation n equals 0 to infinity, negative 1 to the power of n plus 1 times 1 divided by 2n factorial. Let's first check the conditions for the alternating series test. So those two conditions are the terms have to be decreasing in magnitude. An plus 1 is less than an. That means 1 divided by plug n plus 1 for n. So we get 1 divided by 2 times n plus 1. Close off the brackets. Factorial should be less than 1 divided by 2n factorial, which is the nth term. Well, that's true because we're making the denominator larger on the left-hand side, the ratio becomes smaller. So the first condition is satisfied. Let's check the second condition. The limit as n approaches infinity of an should be equal to 0. So we have limit n approaches infinity of 1 divided by 2n factorial, which is the nth term is 1 divided by 2n factorial. And this is going to be 0 because in the numerator we have a constant. In the denominator we have a huge number that's growing to infinity, so ratio approaches 0. That means the two conditions of the alternating series test have been satisfied. This alternating series converges, so we can apply the remainder theorem to find out how many terms we need to add up to find the required level of accuracy, which is 5 decimal place accuracy. So absolute value of Rn is equal to absolute value of S minus Sn is less than 0.123, 5 zeros, and 1. So S is a sum of the entire infinite series. Sn is the sum of the first n terms, is the nth partial sum. The error is less than an plus 1, which is the first omitted term, and we'll make this less than 10 to the minus 6, and then we solve for n. So that's our strategy basically. Now, an plus 1 is equal to 1 divided by 2 times n plus 1 factorial, so that's 1 over 2n plus 2 factorial if we simplify, and this should be less than 10 to the power of minus 6. Now let's expand the series summation n equals 0 to infinity, n equals 0 to infinity minus 1 to the n plus 1 times 1 divided by 2n factorial. So S is equal to, plugging n equals 0, we get negative 1 to the power of 0 plus 1 is 1. Negative 1 to the power of 1 is negative 1. Divided by 2 times 0 is 0. 0 factorial is going to give us just 1. Plus 1 divided by 2 factorial minus 1 divided by 4 factorial plus 1 divided by 6 factorial minus 1 divided by 8 factorial plus 1 divided by 10 factorial minus 1 divided by 12 factorial, and so on. So n equals 0 gives us the first term of this series. N equals 1 gives us the second term. N equals 2 gives us the third term because we're starting the series at n equals 0. Usually we started at n equals 1. And n equals 3 gives us the fourth term. N equals 4, the fifth term. N equals 5 is going to be the sixth term. And n equals 6 is going to be the seventh term. So an plus 1, the first omitted term, is equal to 1 divided by 2n plus 2 factorial, and we need to make this less than 10 to the power of minus 6. That's what the remainder theorem tells us. S minus Sn is less than or equal to an plus 1, and we make this less than 10 to the minus 6, and we solve for n. All right, let's try n equals 3. So we have a4 is equal to, the reason it's a4 is because we're plugging n equals 3 here, 3 plus 1 is 4. a4 is equal to 1 divided by, n is 3, 3 times 2 is 6, 6 plus 2 is 8, 1 over 8 factorial. And this comes out to 0, 0, 0, 0, 4 zeros, 2, 4, 8. This is larger than the prescribed error, larger than 10 to the minus 6. That means n equals 3 doesn't work. Let's try n equals 4. Trying n equals 4, we get a5 is equal to 1 divided by 2 times 4, 8 plus 2, that's 10 factorial. This is equal to 0.1234, 4 zeros, and another 2 zeros, and 2, 8. This is less than 10 to the power of minus 6, because we've got at least 4, we've got 5 zeros here, and the next term is 0. The next decimal place is 0. So n equals 4 will work. That means absolute value of R4 is equal to absolute value of S minus S4 is less than or equal to A5, which is less than 10 to the power of minus 6. So we know that n equals 4 works. But because we're starting the index at n equals 0, we need to add 1 to n, so 1 plus 4 is equal to 5, to get the number of terms required. Because we're starting the index at n equals 0, minus 1 to the n plus 1 times an. And this series starts at n equals 0. We need to add 1. We need to add 1 to n to get the number of terms needed. So we get n plus 1 is equal to 4 plus 1 is equal to 5. So 5 terms are needed. 5 terms needed. So S4 is equal to negative 1 divided by 0 factorial plus 1 divided by 2 factorial minus 1 divided by 4 factorial plus 1 divided by 6 factorial minus 1 divided by 8 factorial. Now this is not a typo, it's S4 because n is equal to 4, but we actually have 5 terms because we start at n equals 0. So 1, 2, 3, 4, 5 terms. So we need to add up the first 5 terms of this series to approximate the sum of this alternating series with error less than 10 to the minus 6. S minus S4 is less than 10 to the minus 6. So if we add this up, this is an approximation for the sum of the series. This will be approximately equal to the sum, and the error of this approximation is less than 10 to the minus 6. We're adding the first 5 terms of the series, and the error is less than the next term, which is less than 10 to the minus 6. So the error of the approximation is less than 10 to the minus 6. All right, thanks.